Hello everyone, and welcome back to my YouTube channel or the Vig Structure Hub. This is the #1 channel for structural insight. Today I want to do summary of timber design to BS5268. Then after here, I will tackle an example or a question from past paper, and this will come from this year paper, July 2025. So stay tuned for that. Why am I doing this? I'm doing this to help those who will be sitting for an exam this November so that they can prepare well to pass their exam. So without wasting any time, let's start the summary of timber design to BS5268. So I want to start by modification factors. Modification factors. So these are factors which modifies the grade stresses for different strength class of a concrete. So number one, I want to begin by K3. So K3. So K3 is duration of loading. So this one is for duration of loading. And this K3 is found in table 16 of BS5268, like that. So we have different duration for modification factor K3. So I will just state the duration for modification K3. So number one, you have the long term. So you have the long term. So long term K3 is equal to 1.0. And then we have medium term. So K3 for medium term is equal to 1.25. And then we have short term. So short term for K3 for short term is given by or is equal to 1.50. Then we have very short term. So K3 for very short term is equal to 1.75. So these are the modification factor K3. And K3, it modifies all the stresses. So modify all the stresses or the grade stresses, like that. So we are done with K3. We proceed to K5. So K5. So K5 is for notched end. Notched end. And this one, we have number one, notch on the top edge. First, it modifies. It modifies only grade sharing stress. Grade sharing stress. And then we'll start by notch on the top, notch on the top edges. So for notch on the top edges, I will use this sketch to illustrate. So this distance is A, and this one is HE, and this one is H. As you can see, this one is a timber joist, and this timber joist, it has been notched at the top, at here, at the top portion, which is this portion. So the distance from here to here is A, and then the distance from here to here is HE. So K5 is equal to H into bracket HE minus A, close the bracket, plus A HE, then all over HE. So this one, it will apply, this K5 will apply when for A is less than HE. So this one will only apply when A is less than HE. So it means this HE is greater than A. And then K5 is equal to 1.04. A is greater than HE. So in case A will be greater than HE, then K5 will be 1.0. So let's proceed to notch on the underside. So this is Roman 2, notch on the underside. So let me use this sketch to illustrate notch on the underside. So as you can see, this one is a timber joist, and it has been notched on the underside of this section. So K5 will be given by this formula. K5 is equal to HE all over H. So HE all over H. And this K5, it must be greater or equal to 0.5. So this is Roman 2, notch on the underside. So let me use this sketch to illustrate notch on the underside. So as you can see, this one is a timber joist and it has been notched on the underside of this section. So K5 will be given by this formula. K5 is equal to HE all over H. So HE all over H. And this K5, it must be greater or equal to 0.5. So it must be greater or equal to 0.5. So this K5 will be used when given a question and the question has a timber joist which either has a notch on the top edge or a notch on the underside. So you'll calculate the K5 for either case, and then this K5 value will help you to calculate the permissible shear stresses parallel to grain, which will be used in design consideration for shear. So we proceed to K7. K7. So this one is the depth factor. So this one, it modifies bendings only. So modifies bending only. So for the K7, we have so the K7 given in the table. So K7 given in the table applies only to sections which has a depth of equal to 300 millimeter. So any other section or any section with a different depth. So sections with a different depth, must be multiplied by K7. Yes, by K7. So I will start by K7 is equal to 1.17. So K7 is equal to 1.17. Here, the depth is less than 72 millimeter. So K7 is equal to 300 over H raised power 0.11, and this one D is greater than 72 millimeter but less than 300 millimeter. So this is the second case. And then the third case, K7 is equal to 0.81 into bracket H square plus 92 300 all over H square plus 56 800. And for this case, H is greater than 300 millimeter. So this is all about K7. We proceed to another factor, which is K8. So K8. So K8 is a load is a load sharing system. So it applies to a load sharing system. So when I'm talking about load sharing system, it means if we have a joist spaced, for example, these are the joist, and they are spaced at a distance of 400, 400, 400. So based on BS5268, all joists that are spaced, or all systems that are spaced below 610 millimeter, then they are load sharing system. So they are a load sharing system. So for this case, for the system which are below 610 millimeter center to center, then K8 is equal to 1.1. 1.1. And for all system above 610 millimeter center to center, then K8 is equal to 1.0. So K8 modifies all grade stresses, like that. So we are done with K8. Let's continue. Let's talk about the design consideration. So number one, I will start by bending. So bending is given by this formula. So this is the design formula. So Z is equal to M over F, whereby M is equal to design moment and F is equal to permissible bending stresses parallel to grain. So this is the design formula. This is the design formula. So our aim is to get Z. If you get Z, then you will be able to go to the table with the value for Z and obtain the section for that value. So also Z is given by this formula, BD square all over 6. BD square all over 6. So we can also easily determine the sections, the suitable size of timber joist when a depth to breadth ratio is known. And then B, so for the first case, if you can be given the depth ratio to breadth ratio, for example, D over B is equal to 3, then it means you can make B the subject of the formula or D. So for example, let's make D the subject of the formula. So we will cross multiply. So it means D is equal to 3B. So this 3B can help you to obtain the suitable size of timber joist. So we proceed to B. B, when either breadth or depth is known, when either breadth or depth is known. So you can be given a question with a known breadth. For example, you can be told a timber joist which has a breadth of 200 millimeters and depth to breadth ratio is equal to 3. So this one is equal to B. It means you can easily find the D. You can easily find the D. So the D will be equal to 3B. So D is equal to 3 times 200, which is equal to 600 millimeter. And then you will check if this size, which is 200 millimeter by 600 millimeter, will support the load which you will be designing for such a joist. So let's talk about shear. So design consideration number 2 is shear. So number 2 is shear. Shear. So the maximum shear which is tau, the maximum shear stress which is tau. So tau is given by 1.5 V over BD, whereby V is equal to maximum shear force. Maximum shear force. And B is the breadth of the section. And D is equal to the depth of the section, like that. So tau, which is the maximum shear stress, must be less the permissible shear stress parallel to grain for such a section to be okay in shear. So we proceed to the design number 3, which is bearing. So number 3 is bearing. So for the bearing, so Q bearing is given by this formula V over Bx, whereby V is equal to maximum shear force, and B is the breadth of the section. So X is the bearing distance. bearing distance. So tau, no, the Q bearing must be less than the permissible stress perpendicular to grain. Permissible stress perpendicular to grain. For such a section to be okay in bearing. So this should be permissible stress in compression. Permissible stress in compression. Perpendicular to grain, like that. So I want to explain this bearing distance. So I want to explain this bearing distance. So if this is a beam, or a joist, and this joist is supported on the wall. So this is the wall, and the distance of this wall is 200. So the bearing distance, which is x, for this case will be 200 millimeter. So the bearing distance will be 200 millimeter, which is the distance or the thickness of this wall. So that is all about the bearing distance. So design consideration number 4, which is deflection. So these are the standard formulas which are used to determine the induced deflection in timber design. So the total deflection is equal to bending deflection plus shear deflection. For example, the first case, this is a simply supported beam with a load at the center. So the total deflection is equal to, the first one is for bending deflection, and then this one is the shear deflection. And then for the second case, this is the formula. So this one is for the bending deflection, and this one is for the shear deflection. So it applies up to this beam, which is a cantilever beam, which is supported on one side. So the total deflection will be given by this formula. So the members below 610 center to center, E, so members below 610 center to center, the E which will be used for such members will be E mean. So E mean will be used for members below 610 millimeters. And the members above 610 millimeters, we will use E minimum. Get the difference? So when calculating deflection, members below 610 millimeters, we use E mean. Members below 610 millimeters center to center, we use E mean. And members above 610 millimeters center to center, we use E minimum. Now let's talk about the effective span. So the effective span is very important for the safety purposes. The span which is used in the design is the effective span. So for number 1, we have simply supported beam. So as you can see, this is a simply supported beam, and this is the wall or the column, like that. So the distance between the inner side of this wall is what we call clear span, as you can see, and the distance between the center of this wall or column to the center of another column or wall is what we call effective span, and the outer distance from here to here is what we call actual span. Since effective span is very important in designing a timber or in designing any structural element, we have to calculate it for the safety purposes. So effective span is equal to clear span plus one bearing. Clear span, this is clear span plus one bearing. So one bearing is the thickness of this wall or column, which I've already shown you. I have already shown you this. So clear span plus one bearing, or effective span is equal to actual span from here to here minus one bearing, like that. So this is a cantilever beam. So this is the wall, like that. So this is the clear span, this distance from here to here, and then the effective span is from here to here. Effective span which will be used in the design. So the effective span is equal to clear span plus a half bearing. So bearing is the thickness of the wall. So a clear span plus a half bearing. Again, there is something that you should understand about design or a timber design to BS5268. So you are supposed to understand the philosophical design behind timber design to BS5268. So BS5268 uses permissible stress design philosophy. So in this philosophy, no factoring of loading. So if you are designing, for example, a timber joist, and you have been provided with loading that will be applied on that joist, you will not factor that or those loads. So you will just get the total loading, and then from there you will calculate the design moment, and then from the design moment you will proceed and select the section that will be suitable for the loading you calculated. So no factoring of loading in this design of timber to BS5268. So let's now proceed to the question from the past paper. We want now to solve a question from past paper, that is July 2025. The question is on the board, and this is July 2025, question number 5. And it reads, Figure 6 shows a loaded timber joist beam. Design the beam, hence check its adequacy in bending, shear, deflection, and the bearing using the data provided. So the question is 20 marks. So these are the data. Grade stresses from table, we'll use strength class 4. And then the permissible deflection is equal to 1 over 360 of span. And then for the K3, we'll use medium term loading. And then K8 is 1.0. So this is the beam. As you can see, it has a point load, and the point load is comprising of imposed and factored load of 6 kilonewton and dead and factored load of 3 kilonewton, and then a UDL of 1.2 kilonewton per meter. So this is the QK. QK is the imposed load. So let's see how you can tackle such a question. So solution. So the first thing to note on this question, we have been provided a beam which has several loadings. So first we have a point load of 6 kilonewton, and this is imposed, which is unfactored, and then 3 kilonewton, a dead load, which is also unfactored, and then 1.2 kilonewton per meter, which is imposed load. So for this one, we have not been told if it is unfactored or factored. So we'll assume. So assume, make sure when you assume, you write it on your exam booklet. So assume 1.2 kilonewton per meter, which is QK, is also unfactored, like that. So after doing so, remember what I have just told you, that the BS5268, which is the design of timber, the philosophy which is behind the design is called permissible stress design. So in permissible stress design, we are not supposed to factor the loading. So we will just use the service load, the way the load is on that beam. For example, we'll just use 6 kilonewton, 3 kilonewton, and 1.2 kilonewton, the way they are, without factoring. So don't factor this loading. So if we come to a point load, so you'll say point load. So you'll get the total of the point load, which is 6 plus 3. So this one is equal to 9 kilonewton. And then the QK, and then the UDL, which is the QK, is equal to 1.2 kilonewton per meter. Just use the way they are. And then after doing so, you will come and draw another beam. So draw another beam. And this 9, or this point load, it will change to 9 kilonewton. So the point load will be the total point load on this beam. And then you have the UDL, which is 1.2 kilonewton per meter. And then the span, or the effective length, is 2.4. So remember, examiners, they test you in so many, they want to see if you know exactly what you are doing, because if you are told in this question, these loads, they are unfactored, so some of you may go ahead and factor this load. But because of the philosophy behind this design of timber to BS5268, it uses the permissible stress, then you are not supposed to factor the loading. Just use the way they are. So they may test you in various aspects, as you have seen in the question. Now, from this beam, you can calculate the maximum bending moment, or the maximum design moment. So M max will be given, if we start with UDL, the formula is W L square all over 8. And then we come to the concentric load, which is point load at the center of the beam. So this is WL all over 4. Remember, I'm using the formulas because the point load is at the center. The point load is at the center. But what if the point load is not at the center? If the point load is not at the center, do not use the formulas. You can use uh, the three equation of equilibrium to come up with a reaction, for example, reaction A and the reaction B. And then from there, you can draw the shear force diagram. And then from the shear force diagram, you will determine the maximum shear force. And then from there, you will also determine the maximum bending moment, which will be used in the design of such a beam. So for this case, let's use these formulas to avoid a lot of time. So allow me to clean here, but this information, we will use them later in our calculation. For example, the permissible deflection, you can put it somewhere, 1/360 times span, and then K8 1.0, and then the K3 is the medium term loading, like that. So M max, or the maximum moment, is equal to, if we start with UDL, the W is 1.2 times L. L is 2.4 plus 2.4, which is 4.8, then square all over 8, then plus W. This is for the point load, so W is 9 times L is again 2.4 plus 2.4, which is 4.8 all over 4. So the answer is equal to, answer is 14.256 kilonewton meter. And then after calculating the M max, we'll also calculate the shear force. So the maximum shear force, which is V, so the maximum shear force is equal to, if we start with UDL, so this one will be WL over 2 plus a point load W all over 2. So this one is equal to 1.2 times L 2.4 plus 2.4, 4.8 all over 2 plus 9 all over 2. So this one is equal to 7.38 kilonewton. So this one is for V, 7.38 kilonewton. So let's now proceed to modification factors. So we'll start by K3. So K3, you were told in the question, the loading is medium term. So for the medium term duration, K3 is equal to 1.25, like that. And then K8, we have been given K8 as 1.0. So K7, we don't know K7 because we don't know the section size of this timber. So the grade stresses, we proceed now to grade stresses. And this one will be obtained from strength class 4. So I want you to read these grade stresses on your own. So I will not show you how to read it, but I will just give you the value. So the bending parallel to grain is equal to 1 point. Bending parallel to grain is equal to 7.5. 7.5 Newton per millimeter square. And then compression perpendicular to grain is equal to 1.9 Newton per millimeter square. So E minimum is equal to 6600 Newton per millimeter square. And why am I using E minimum? Because our K8 is 1.0. So from the summary, I said that when the joists are placed below 610 center to center, we will use E min. And here, K8 is equal to 1.1. But when the joist or any system is above 610 center to center, we'll use E minimum. And K8 is equal to 1.0. So this 1.0 is what has guided me to use E minimum. You can be guided by the spacing of the joist or system like that. So allow me to show you the table. Let me just show you the table. Let me show you the table so that you may know how to read the table. So this is the table. As you can see, we have strength class 1, 2, 3, 4, 5, 6, and so on. So we'll proceed to strength class 4, as you can see, and then bending parallel to grain is 7.5. As you can see on the board, you have it. And then compression perpendicular to grain, compression perpendicular to grain, not parallel, perpendicular. The same class, which is 4, and we will use 1.9, use the value which is lower, don't use 2.4. So 1.9 Newton per millimeter square. And then we'll come to just follow the cursor to E minimum, which is 6600 Newton per millimeter square. So that is how you read that table. So let's now proceed to permissible stresses. Permissible stresses. So we will start by bending parallel to grain. So stress in bending parallel to grain, the permissible stress will be 7.5 times K3. K3 modifies all the stresses times K8. K8 modify all the stresses times K7. So K7 is for bending only. So this one is equal to 7.5 times K3, 1.25 times K8, 1.0, and then ignoring K7 because we don't know the section. So ignoring K7. So this one is equal to 9.375 kilonewton per Newton. per millimeter square. And then you proceed to compression perpendicular to grain. So this one is equal to 1.9 times K3 modify all the stresses times K8. So K8 modify all the stresses 1.9 times K3 1.25 times K8 1.0. So this one is equal to 2.375 Newton per millimeter square. And then you proceed to stress in parallel perpendicular to grain. So this one will be 0.71 times K3 times K8, which is equal to 0.7 times 1.25 times 1.0. So this one is equal to 0.88 Newton per millimeter square. So these are the permissible stresses. We proceed to design consideration. So allow me to clean here. So design consideration. So number one is bending. So for bending, we know that Z is equal to M over F. So this one is equal to, our M is the moment, the design moment we calculated based on the loading on the beam. So this one, it was 14, or it is 14.256. And then because it is in kilonewton meter, we will multiply by 10 to power of 6 to make it Newton millimeter all over F. So F is here. We'll use F as a bending stress parallel to grain, which is 9.375. So you will say ignoring K7 because we don't know the section. So this one will give us 1.52064 times 10 to power of 6 millimeter cubic. So which is the same as 1520.64 times 10 to power of 3 millimeter cubic. So in the table, that is given to 10 raised to power of 3 millimeter cube. So this will help you to select a section from the table. So then from the table, Z provided from the table, find the table and read the section size from that table. So from the table, Z provided is equal to 150 by 300 millimeter, and Z is 22 50 times 10 to power of 3 millimeter cubic. So from the table Z provided, this is now the size of the timber section, 150 by 300 millimeter, and Z from the table is 2250 times 10 raised to power 3 millimeter cubic. So this one should be slightly higher than this. Should be slightly higher than this. So let's continue. So remember, our initial Z was 1520.64 times 10 to power of 3 millimeter cubic. Then ignoring, so this was our Z ignoring K7. Since we have the section size, which is 150 by 300 millimeter, so this one is D and this one is B. So we can use this D to find the value of K7. So the value of K7 will just be 1. From the guideline provided in the table or in BS5268, if D is equal to 300, then K7 is equal to 1. K7 is equal to 1. So it means Z required will remain the same, will be 1520.64 times 10 raised to power 3 millimeter to the power of 3, which is less than Z provided. And Z provided is this Z from the table, which is 2250 times 10 to the power of 3 millimeter cubic. Therefore, section OK in bending. And then from there, we check for other design consideration. So I will proceed to design consideration number 2. I now proceed to shear. Number 2 is shear, like that. So for shear, Q is equal to 1.5 V over BD. So this one is equal to 1.5. Remember our V is 7.38. Then this 7.38 is in kilonewton. So multiply by 10 to power of 3 to make it Newton over B. Our B is 150 and our D is 300, like that. So this one is equal to 0.246 Newton per millimeter square. So it means 0.246 Newton per millimeter square is less than the permissible stress, the permissible shear stress. So it's less than the permissible shear stress, and this and it is 0.888 Newton per millimeter square. So it therefore means section OK in shear, like that. We proceed to bearing. Number 3, design consideration number 3 is bearing. So Q bearing is equal to V over Bx. V over Bx. But since we have not been given x, assume a bearing of 200 millimeter thick wall. Therefore, is equal to 7.38 times 10 to the power of 3. Change it from kilonewton to Newton over B, which is 150, times 200. So this one is equal to 0.492 Newton per millimeter square. So 0.492 Newton per millimeter square is less than the permissible compression stress, perpendicular compression stress. So which is 2.375 Newton per millimeter square. Therefore, section OK in bearing. So 0.492 is less than compression perpendicular to grain, which is 2.75 Newton per millimeter square. So section OK. So we proceed to the last consideration, which is deflection. So deflection. So permissible deflection is equal to span over 360. And span and our span is 4.8 meters. So convert it to millimeter, multiply by 1000 over 360. This one will give us 13.33 millimeter. Induced deflection you will do the induced deflection, and then you will compare the permissible deflection with induced deflection, and you will conclude whether it will fail or it will be okay in deflection. So that is for you. I leave it at that point, and that marks the end of the question. If you have not subscribed to the channel, please subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. So thank you for your time, and we meet again in my next session.